Hello, everyone, and welcome back to The Explainer. Today, we're doing something absolutely brilliant. We are going to decode the vast and honestly sometimes intimidating world of organic chemistry right here on our board. If you've ever looked at a massive chemical structure and felt a bit overwhelmed, don't worry at all. By the end of this, you're going to see that all these giant molecules, they're just built from incredibly simple, predictable patterns. So grab your notebooks, get comfortable, and let's master functional groups together. Here's our roadmap for today. First, we'll meet the functional groups, then look at single bond replacements, followed by nitrogen and sulfur groups. After that, we'll tackle the carbonyl family, and finally wrap up with acid derivatives and beyond. Let's get straight to it. All right, section 1, meet the functional groups. Okay, let's establish our absolute fundamental building blocks. Everything starts right here. Whenever you look at organic chemistry formulas, you'll constantly see the letter R written on the board. So what is it? Well, R stands for an alkyl group. Just think of an alkane, a standard carbon chain, but it's missing exactly one hydrogen atom. Because it's missing that one hydrogen, this R group is basically a blank canvas. It is highly reactive and literally just waiting to attach to something new. This R is the foundation of everything we're doing today. And this brilliantly shows our core mechanic for today. How do we actually make all these different chemical families? It's a super simple 3-step process. Step 1, you take an alkane. Step 2, pull off a hydrogen atom. And step 3, replace it with a new functional group. That's the whole secret. Just swapping out a single hydrogen creates an entirely new chemical family with totally different rules. It's like chemical Legos, isn't it?
Moving on to section 2, single bond replacements.
Let's see how this builds when we make our easiest single bond substitutions. We're going to start by bringing oxygen into the picture. Imagine we have our alkyl group, RR, and we replace that missing hydrogen with a hydroxyl group, an OH. Suddenly, boom, the family becomes an alcohol. The general representation is just ROH. But what if we do something a bit different? If we take an oxygen atom and sandwich it directly between two R groups, we get an ether. The structure is an oxygen single bonded to 2 carbon chains, written as ROR. It's wild how just playing with simple single bonds creates entirely different chemical properties.
All right, section 3, nitrogen and sulfur groups.
So oxygen obviously isn't the only player in this game. Let's step up the complexity a notch and see what happens when nitrogen and sulfur join the party. When the hydrogen of an alkane is replaced by an amino group, and an NH2, we get a primary amine, written as RNH2. Now, what if we use sulfur instead of oxygen? Well, if we attach an SH group to our R chain, the family becomes a thiol. And for something a bit bulkier, if we replace a hydrogen with an SO3H group, we get a sulfonic acid. The underlying logic is exactly the same. We are just snapping different functional blocks right onto our base R chain on the board. Now, what's really fascinating here is the subtle flip in the structure. Both of these involve carbon and nitrogen triple bonds, but the connection point changes absolutely everything. When the R group connects directly to the carbon atom, which is then triple bonded to nitrogen, we call it a cyanide. But if we just flip that functional group around so the R group connects directly to the nitrogen, which is then triple bonded to carbon, no way, it becomes an isocyanide. One tiny flip of the attachment point, and you've got a completely different functional group on your hands.
Next up, section 4, the carbonyl family.
Now we're really stepping up the complexity and introducing the mighty carbonyl. A carbonyl is simply a carbon atom double bonded to an oxygen atom. And let me tell you, it is central to so much of organic chemistry. Let's compare 2 closely related cousins. Take aldehydes. Here, the carbonyl carbon is attached to our R group on one side and capped with a simple hydrogen atom on the other, so it's RCHO. But look at ketones. In a ketone, that central carbonyl carbon is sandwiched straight between 2 R groups. There's no terminating hydrogen at all. It's written as RCOR. Basically, the position of that carbonyl group, whether it's at the very end of a chain or stuck in the middle, totally determines if it's an aldehyde or a ketone.
And we can build even more on that carbonyl foundation. If we take our carbonyl group and attach an OH directly to the carbon, we create a carboxylic acid. That's RCOOH. This is an incredibly common, absolutely crucial functional group. But watch the board carefully for this one. If we sneak in just one extra oxygen atom right between the carbonyl carbon and the OH group, the structure becomes RCOOH. That extra oxygen transforms the whole family into a peroxy acid. Just one extra atom, and it's an entirely new classification.
Finally, Section 5, acid derivatives and beyond. For our final manipulations in this explainer, let's take that carboxylic acid we just learned about and form even more complex derivative families. Starting from the carboxylic acid structure, if we remove the OH group entirely and swap it for a halogen, like chlorine or bromine, which we represent with an X, we create an acid halide. The structure becomes RCOX. But what if, instead of a halogen, we swap that OH for an RNH2 amino group? Well, then the family becomes an amide, written as RCNOH2. Again, we're literally just playing chemical Legos here on the board, substituting one piece for another.
Let's check out 2 more acid derivatives. If we go back to our carboxylic acid and replace the hydrogen of the OH group with a whole new R group, we make an ester. This is mapped out as RCOOR. And to put this into perspective, esters are the exact functional groups that give many fruits their wonderful sweet smells. It's amazing. Next, what if we take 2 carboxylic acids and join their carbonyls together through a single oxygen atom, losing a water molecule in the process? We get a bulky acid anhydride, represented as RCOOCOR. Now, before we finish up, we've got to rapid fire our final structural classifications. These are based strictly on carbon-to-carbon bonding, without needing any outside elements like oxygen or nitrogen at all. When an alkane chain develops a carbon-to-carbon double bond, the family name becomes an alkene. And when it develops a carbon-to-carbon triple bond, it is known as an alkyne. These multiple bonds actually act as functional groups themselves, because they are sites of really high chemical reactivity. And that brings us to the end of our tour. We've systematically swapped atoms and groups on the board today to build nearly 20 different chemical families, from simple alcohols all the way to complex acid anhydrides. So I want to leave you with this final question to think about. How do these tiny, simple structural swaps dictate the fundamental chemical reactions of the entire physical world around us? Think about it. Every single medicine you take, every fabric you wear, it all reacts the exact way it does because of the specific functional groups we just mapped out. I really hope this structure helps you master your chemical reactions moving forward. Keep learning, and I'll catch you in the next explainer.